m plus 1 to the kth power.
It's time to stop! It's time to stop, okay?
Good morning, fellow mathematicians! Welcome back to another episode of almost, in parentheses, impossible integrals. Something serious. Only focusing on the integrals right here. So please support the creator, Cornel, right here, okay? Link to the Springer store and Amazon and ebooks down there in the description. Seriously, so support the creator. He's such a nice guy and he wrote such a great book. He's so good at integrating, probably way better than me at integrating stuff, okay? He's just so fabulous. Go support the creator, please. Do not pirate those PDFs. Just buy the book, it's seriously worth it. We are going to take a look at the second integral, the second integral of this very book. This thing right here. It looks kind of fancy, and it's really fancy. When I first did it, I was using the gamma function, but his way is way cooler, because if you take a look, this is a sequence of integrals in the natural numbers n and m, and you can solve such things using recurrence relations, basically, doing some really fancy things. I have done this before with the Fourier kernel and the Dirichlet kernel integral. It's so Gucci. That's why we are going with your way, Cornel. And we're going to dive right in. At first, I would like to get rid of the parameterization up here, the t in the upper bound. How can we get rid of it? Meaning, how can we turn it into some kind of real number? Well, we are going to eliminate it using substitution. We have done this before with various integrals. So let's choose a cool variable. Let, for example, new. This is a new, okay, this is a new variable that we haven't used before. It's not a mu, it's a new. Let new be equal to, well, in this case, x over t, okay? You are going to see why this is good, why we should use that. Well, if we plug 0 into here, our lower bound is going to be just 0. If we plug t into there, it's going to be t over t, which is nothing other than 1. I'm going to vary today a little bit between nothing but, nothing other than, nothing else, okay, that's the wrong thing, or nothing more than, okay? So our differential thus is nothing other than, oh, this is so fancy, this is such fancy English. T, d nu, is thus nothing other than the x. We can plug all of this in. Our x, if we multiply by t, is not equal to 0, is the upper bound of an integral, meaning it's strictly greater than the lower bound in normal case. Yeah. Then x is nothing but nu times t, leaving us with nu to the mth power, t to the mth power, times the Logarithmus naturalis, natural log to the nth power of x, once again, is nu times t, and then t d nu. Now, gladly, our t, our parameterization, is not with respect to our integral, okay, not with respect to our nu, our variable we are integrating over, meaning it's just a constant. Using the linearity of the integral, we can bring it to the outside as t to the m plus 1th power times the integral, 0 to 1, nu to the mth power. And now we are going to do something really fancy. We are going to rewrite this really nice notation, natural log, as this, to the nth power. Why are we doing this exactly? Well, here comes something that I haven't really used before in an integral. It's the binomial theorem. I did do so in my calculating digits of pi video. It was absolute dog shit, but we have used it there before. Okay, I haven't made a formal proof on that using the principle of mathematical induction. It's boring, so I'm not going to prove it. Okay, but it's something you can see using Pascal's triangle, meaning natural log of nu times t is just the natural log of nu plus the natural log of t, okay, multiplication of the arguments of natural log, but this time to the nth power, d nu. This is just how the function equation of the natural log works in the real numbers, and also kind of in the complex numbers, but not in all cases. Now, binomial theorem, like I said, we are going to apply it to a thing. How does it look like exactly? Well, our first part is going to be preserved. Now, we are going to end up with a summation, okay? You know how this works. A plus b squared is nothing but a squared plus 2ab plus b squared. This is the binomial theorem, but now the generalized version. We are going to have a running index. Let's call it k. It runs from 0 to n. Also, we are going to have n over k. Now, we are going to count our binomial parts, our powers basically. So the natural log to the kth power of nu, okay, it's symmetrical, you can also rewrite it, and interchange those. Okay, you can just interchange those, and then you are going to end up with different powers, but we are going to take the easy route right here. And then natural log to the n minus kth power of t integrated with respect to nu. You have probably seen it before, the binomial theorem. If you didn't, then go back to your anal class and take a look at that yet again, once again. Now, the good thing is that's a finite summation, meaning we don't have any problems with convergence with limits right here, meaning we can simply use the linearity of the integral to, well, drag this summation to the outside. Also, we have some independent stuff right here, n over k, and n choose k, not n over k, that's n choose k. I'm thinking German right here, I'm terribly sorry, and this natural log with respect to t. Meaning, let us bring this to the outside. We are going to be left with t to the m plus 1th power. This finite t boy, and then we are going to have n choose k. The logarithmus naturalis n minus k of t, and then integral from 0 to 1 of nu to the mth power, natural log to the kth power of nu d nu. And here comes the part in that I have praised at the beginning of the video, the really cool recursive thing. We are going to give this thing a new name. As you might notice, that's just yet again a sequence of integrals. It's a new integral we have right here, and we are going to give it a new name. That was so meta. Okay, we are going to call it I, as I always do, of m comma k. You can also write it as I parentheses m comma k as a multivariable function. I really don't care, okay? But now we are going to solve this thing right here using really fancy integration by parts. Maybe you have never seen this before. It's a really fancy way to write out integration by parts basically. I of m comma k is thus nothing but. We did this a lot before. Finding the antiderivative of natural log is not too trivial, meaning we are going to differentiate it, this part. Also, integrating polynomials is indeed a really trivial, marginal, redundant thing to do. No, it's not really redundant, we have to do it. Nu to the mth power, we are going to integrate it. Meaning, I'm going to put it here. We are going to have our differentiation and our integration, differentiating the natural log to the kth power of nu is going to give us. Okay, at first, we are going to use the power rule. We have to drag the k to the front and reduce the power by 1. K times the logarithmus naturalis to the k minus 1th power of nu. And then times the inner derivative, which is nothing other than nu, 1 over nu in this case. Also integrating our nu to the mth power is going to result in nu to the m plus 1th power over m plus 1. Maybe you can already see where this is going. This is so nice. It just puts a smile on my face. It's so much fun. We're going to multiply this together, and then we're going to take the integral of this thing and do some arguing on the upper and lower bounds, and then we already came pretty far. I tell you this much. Natural log of nu to the kth power times a nu over m plus 1 evaluated from 0 to 1 minus k over m plus 1 is just a constant. We can bring it to the outside using the linearity of the integral. Also, in the integral, we are going to have the natural log to the k minus 1th power of nu times nu to the m plus 1 over nu, leaving us with nu to the mth power. Ah, this is the really cool part. Okay, next, integral. K, I'm terribly sorry, not n, over m plus 1 times integral of nu to the mth power, natural log to the k minus 1th power of nu d mu. Oh, this is so nice. This is really nice. Can you see why this is exactly so nice? Okay, if we take a look at this integral right here, just a single little integral. What is this exactly? Let us compare this with the first one we have. with I of m comma k. Well, we had m as the exponent of our nu right here, and we had k as the exponent of natural log right here. But this time, we are going to have I of m comma k minus 1. Meaning, what we do, we are going to preserve our m right here, and we are going to reduce our k index by 1 each time we do integration by parts, basically. Isn't that really cool? Meaning, this thing right here is I of m comma k minus 1. And thus, we have found a really nice recurrence relation. It's like a reduction formula. You could say it's really cool. It's really cool. Now, we have this thing right here. What can we say about this? It's going to vanish. Going to take y. If we plug 1 into here, also I forgot the mth power. If m plus 1th power really doesn't quite matter. Now, if we plug 1 into here, well, natural log of 1 is going to vary to 0. It's going to vanish. Now, if we plug 0 into here, natural log is going to go to negative infinity to the kth power. So it's kind of negative infinity, something infinity. And also we are going to have mu being equal to 0. Negative infinity or infinity times 0 situation is something you can use L'Hopital on. And I have done this kind of situation before with like e to the something kth power. And I tell you this. You can do k iterations of L'Hopital on here, and you're going to see that overall, intuitively speaking, our natural log is going to grow way slower than any polynomial in our nu right here. Meaning our nu is going to approach 0 way faster than our natural log is going to approach infinity in any way. So more formally, you can probably also expand this into a Taylor series, for example, or you can just do L'Hopital k iterations exactly. No matter what you do, you're going to arrive at the conclusion that this is going to vanish at the lower bound, meaning overall, this is going to vanish. And this is going to provide us with a really, really nice result, namely that I of m comma k is negative k over m plus 1 times I of m comma k minus 1. We are going to divide both sides by this term to be left with a really nice discrete expression right here. Okay, so that's equivalent to saying I of m comma k over I of m comma k minus 1 is thus nothing but negative k over m plus 1. And here comes integration by parts in a really, really fancy way. Now it's going to go really nicely. Okay, we have a recurrence relation right here, and you see, if we compare the index, our m is going to be preserved all the time, meaning in each member of the sequence in this form, we are going to be left with 1 over m plus 1. Also, our negative sign is not really changing. There's no way why this would change right here. And our k, well, our k is the same index as this right here. You can do another iteration of integration by parts. Meaning, if you were, for example, to take a look at I of m comma k minus 1 over I of m comma k minus 2, you are going to be left with negative k minus 1 over m plus 1. How does this help? Well, why not take a look at the multiplication of all those members after doing exactly k iterations? Why does it make sense to do, k minus 1 iterations? Or is it k? Yeah, k minus 1 iterations. Why does it make sense to do k minus 1 iterations? Well, then we are going to be left with I of m comma k minus parentheses k minus 1, so that's I comma m, I of m comma 1, I'm terribly sorry, over I of m comma 0 in this case. And this is the last member in the sequence when it comes to our k. Meaning if our k is going to be equal to 0, our natural log is going to vanish in the process if we compare it with our original one. Meaning we're just going to integrate a polynomial in our nu right here, and this is really easy to do. So let us see what we get at. We are going to take a look at all those members in the sequence. We are going to multiply them together just because of one simple, really nice thing. Okay? I of m comma k over I of m comma k minus 1 times the next member in the sequence I of m comma k minus 1 over I of m comma k minus 2. Ah, this is so fabulous. Can you see why this is nice? K minus 1 iterations up until I said it, I of m comma 1 over I of m comma 0. So cool. this and that is going to cancel out. Next one is going to cancel out, and next one, up until 1 over I of m comma 1 and I of m comma 1 is going to cancel out. Overall, we are going to be left with I of m comma k. Remember, this is the thing we want to find out. That's the basic thing we want to find out right here. Over I of m comma naught. Meaning, if we could just find I of m comma naught, we would basically be done, because we know what this chain right here, this multiplication, is actually equal to. Well, it's just a multiplication of those members multiplied together, k minus 1 iterations. Meaning overall, this is negative k over m plus 1 times, like I said before, the next one is negative k minus 1 over m plus 1 is going to be preserved. K minus 1 iterations up until, I'm going to put it here, negative 1 over m plus 1. And this is just absolutely nice, because now we have negative 1 to the k minus 1th power. This is what we have, or k plus 1th power, it really doesn't quite matter, it's an equivalent formulation. Also we have 1 over m plus 1 to the k minus 1th power, and also we have k times k minus 1 times k minus 2 up until blah blah blah, 2 times 1, that's just k factorial, okay? Isn't that cool? We are going to be left with I of m comma k over I of m comma naught being equal to negative 1 to the k plus 1th power. I'm going to put a plus 1 right here because I prefer this over everything else. K factorial over m plus 1 to the k minus 1th power. And like I said, all that's really left to do is to find out what I of m comma naught actually is. And this is a really trivial thing, because I of m comma naught is nothing but the integral from 0 to 1. If we take a look at this thing down here, so if you still have it in your head, nu to the mth power d nu. Meaning, if we integrate that, we are going to get nu to the m plus 1th power over m plus 1. Evaluated at 1 is just 1 over m plus 1. And evaluated at 0, it's just going to vanish. So this is going to give us 1 over m plus 1. Meaning, we thus have m plus 1 times our I. I'm just going to denote it like this. We can divide both sides by m plus 1. It's not equal to 0. Meaning, we are just going to get rid of this negative 1 right here. And this is what we are going to be left with. Meaning overall, our original integral that we had right here is this expression times I of m comma k. I have my nice and trustworthy boy right here. We had that this is now negative 1 to the k plus 1th power, k factorial over m plus 1 to the kth power.
It's time to stop! It's time to stop, okay?
Psst, Jens from the future, right here, okay? I actually counted in the wrong way. I don't know why I did that. Please get rid of the plus 1 right here. And please put a plus 1 right here. I was actually counting in the wrong way. For some odd reason, I thought we are going to get k minus 1 iterations, but we actually get k iterations. So if you let this run from 1 to 3, you're going to get 1, 2, and 3. Okay, 3 in total, meaning m plus 1 to the 3rd power, in this case, kth power. I'm terribly sorry for that. Et voila. Isn't that a really crazy expression? It's such a weird generalized integral. I for myself never stumbled upon this thing before, but it's something that's probably pretty prominent in some kind of mathematical or physical context. But here, this integral evaluates to this monstrosity. I thank you guys for watching. If you did enjoy this video, please like and subscribe, and buy Conan's book. Also, buy those t-shirts I created. I hope my shirt did not rub against my microphone. That would be sucky, fucky, okay? And yeah, what else can I say? Support channel on Patreon. whatsoever. I already thank you guys for watching. I'm until the next video. Have a flammable day. See ya.
Mm-mm.